Okay, so most people seem to get it working now. So what you should be working on is you should have a look at the parallel IO exercise sheet, but also I'd initially say you should have a quick read of what's here. But what I will do is I will basically, if I have the parallel exercise sheet myself, I will just, what I will do is I'll now share so hopefully you can see my terminal. It's really not working very well here. Sorry, the application sharing is not working well. Try again. There we go. Okay, fine. So what I should be able to do is I should log in 048 DSH. Oops, log in. So if I look where I am in home, I have to change to /work/TA048/TA048, and then your username, which for me is TA048DSH, but for you will be your, so it's work TA048 TA048, and if I do DF, you'll see that we're actually on work 3. So we're actually on work 3, which has 3.3 petabytes of what only 125 terabytes are used. So I actually have the bench IO here, so I'll do an old, okay. So that's just getting rid of the old one. What you want to do now is, if I can git clone, I go to IO, you'll see there's lots of stuff here, including the README file. But the first thing you need to do is you need to basically set, as it says in the exercise sheet, what it says on the GitHub page is the striping of each file. So if I actually do lfs get stripe on striped, we'll see that it has a stripe count of 1, okay, which is not what we want. Okay, so you'll see the instructions are first with lfs set stripe. We're not going to use these directories at the moment, but unstriped, 1 for unstriped. Okay, this is all in the, this is on the exercise sheet. I'm going to do 2 for striped is I would say 2 for striped. You can use anything you want, but I'll do 2 or 4, but I think 2 is better. And then for full striped, you want to -1. So now if we do lfs get stripe on full striped, you'll see that it now has, it says, that's a bit weird. No, okay, that's a bit, it's okay. So I find it easier to do the get stripe on a file. So if we create a file, I find it easier to do it on a file. So I create some actual files here. If I do lfs get, I find to get the striping information in the directory a bit hard. Unstriped /test.dat, so that's stripe count 1, okay. If I do striped /test.dat, stripe count 2, which you expect, and full striped test.dat, stripe count 12, and it tells me all the that they're set up on. So it's this stripe count you want here. So so it's easiest to set the striping on the directory, but actually when you get the striping, I find it easier to do it on an actual file. So that's all set up now. Okay, now we need to do module, do some loads, cray HDF5 parallel, this is in the Cray NetCDF, HDF5 parallel. That's because I'm not going to use it to write the, oh, what did I do?
No, HDF5 parallel is one.
Is HDF5 parallel is one word. I should have read my instructions. And now we can just do make, and it's actually make minus def make file archer2, actually follow the instructions. Okay, so that should be there. And we have, where is it? Bench IO is there now. If I show you the script, which is called ARCHER2.job, okay, it's going to run on one node and one task per node. It's just going to do, this is going to do serial IO. We have a reservation, and this is the reservation number. I reload the modules just for safety. I'll come back to this magic setting here, but what I do is I run my my account. I run my thing, and this is running the bench IO for a 512 by 512 by 512 array, which, if you work it out, is a gigabyte. It's 512, but each entry is 8 bytes, so that's actually 1024 cubed, which is a gigabyte. I'm going to do local, which means that this is a local size. You can specify it as a global size for weak or strong scaling, but I'm going to do the serial IO, and I'm going to write to the unstriped directory. So following instructions, I just do sbatch archer2.job. If I do ls minus l unstriped, we'll see at some point it should appear. I may not see it actually, because it may. Okay. Oh, that didn't work. I think I just missed it. But okay, so you'll see that I ran this, and it says simple parallel on one process is running on one node. The process grid is what? It's all trivial, of course, because it's a, but you'll see it'll be more interesting one by one by one. The array size is 512 by 512 by 512. So the local array size, the global array size, of course, still the same. Total amount of data is 1 gigabyte. Using the following IO methods, serial, using the following stripings, unstriped, and I took 0.8 of a second to write 1 gigabyte, which is 1.2 gigabytes per second. And that, so first of all, I think you should just run that and check you get that figure. And that's a useful figure to have. You're seeing that if you just open a file and do an F write from a single process, you're getting about a gigabyte a second, which isn't very good. Well, it's not brilliant, but that's your kind of a ballpark. And what we want to do is we want to do better from that. And you'll see the subsequent exercises think about how you can do better than that by writing to multiple from multiple processes to saturate the node, and then maybe writing for multiple nodes. So there are specific examples on this sheet for what to do. You don't need to at this point. You don't need to edit the bench IO program. You just need to edit the script. So we'll let you play around with that. Hopefully the instructions are reasonably explicit. If there are any problems with the instruction, please let me know, because it's the first time I've run these exercises. So okay, so it'd be good to sort of share some results here. What did people get? I mean, we're able to, if anyone got any results. So did you get what did you get the same about 1 gigabyte per second as I did? Does anyone have any numbers that they would like to put in the chat? Okay, fine. And right, so it's about 1.2 gigabytes per second. So that's a useful figure. But from a node, did anyone? What about the I/O from a node, a single node? Did anyone get the second answer? I can actually maybe run that myself, but you should have got more than that, a lot more than that. Did anyone else get the? Okay, 14. Right. So 14.5 is more like what I would expect. Okay. So the question is, yeah. So that node is able to write to 12 disks. Yeah. So that number looks like a single OST can support about 1.2 gigabytes per second, but when we do 128 CPU cores, they're all running to multiple OSTs, and that looks like it's 14.5. But that's not correct. It's a coincidence, because if you do that, did anyone try the nodes equals 2? Right, 25 exactly. So what I would conclude from this is that the maximum I/O bandwidth you can get from a single node is about 14 or 15 gigabytes per second. Yeah. So a node can do about 14 or 15, but two nodes can therefore do about 25, 28, and so you cannot saturate the OSTs from a single node. But we can see we've got a 25, and I thought I'd put an exercise in here to do maybe on 4. Oh, I thought I did. Okay, I don't know if anyone tried nodes equals 4. I'll try that as well, just to, okay, I'm doing the wrong thing. So I think the reason that you maybe got yeah, 49.7 nodes equals 4. So you can see that actually that's so you can see that an OST seems to be able to support at least 4 gigabytes per second. If you could try nodes equals 8, that would be really useful. And then we could, because I think this will give us the sort of ballpark figures for and this is something I only actually found out in the last couple of days when preparing for this course, that we're able to get these figures quite nicely. Okay, so you're getting up to, oh, that's more than I would, okay. For nodes equals 8, okay. So it looks to me that we're still Okay, okay. So it looks like we're not anywhere near saturating the OSTs. The node, it's the limitation here is the bandwidth out of a node, which is of order 10 gigabytes per second. So it's going up and up and up, which is very interesting. Okay, so that's interesting. So so I'll go on to the next lecture, but I think that the take I'll try and prepare I didn't have a chance to do a summary of performance results, but okay. That's more than I expected, actually. Now, there could be some caching going on here, but I don't think so. So I'm supposed to my job is okay. So I'm getting some problems here. Okay, fine. Okay, so I was getting that as well, 78 gigabytes per second. There could be some caching there, but you can see that the important point I think you can see here is that that the bandwidth from a single process is only about a gigabyte per second. The bandwidth from a node can go up to about 10 or 12 gigabytes per second. That's presumably the network interface from each node. And then if you do multiple nodes, we keep going up and up and up. So we're nowhere near saturating the OSTs, the disks. So the bottleneck seems to be a process is slowest, then a node, but the disks themselves seem to be actually much more, the OSTs seem to be able to handle a lot more performance. Is there any questions on that? Sorry, it didn't quite work as smoothly as I'd hoped. Okay. So when I do 16 nodes, I get the same.
The same.
So I will actually edit. I will show a slide. So these are really useful numbers. Which I said I previously, until developing this course, had not understood the I/O system on ARCHER2 because I had assumed it was similar to Archer, and that is not true. So I will now, if I can. I will basically share the sharing is only working every other time yes, that should continue. Yes, so I think that's why I think you were getting the I think that's why you're getting the same. Some people were getting the instructions weren't perhaps quite clear enough that you need to do proc. Yeah. So I would say single process serial. One node we got about 14, 2 nodes, we got about 25. 4 nodes, we got about, I can you look at the 50. 8 nodes, someone got about 75. And 16 nodes I just ran, and I also got 75. So oops, a daisy. Each OST looks like it's doing about this 12, about 6 GB per second, something like that. So you know, does that make so? I mean, I think that I'll try and it seems to be useful figures that up till 8 nodes we're saturating the we still can't saturate the up to 4 nodes we're not saturating the OSTs because we're still limited by the 12 GB per second. So those are interesting numbers. So you know, it looks like a single node can get 14 GB per second until we saturate all the OSTs, which seem to each be able to do about 60 GB per second. So we're getting about 75 GB, which is pretty impressive, actually. So what I wanted to do now, are there any questions on that? So you're right, David. I actually should maybe have, yeah, okay. That's I should maybe make a note of that. That's. So, you know, this is all we're doing. I mean, the bench IO code is relatively sophisticated, but this is literally, you could have done those studies yourself with a 5-line program, open file called rank0.rank1.dat, fwrite a gigabyte, close file, and yet we get very, very, oh, so you did get, okay, it could be depending on other users' usage. Yeah, it could be. It could be. There could also be caching going on, that you may get higher. I don't quite understand how the caching works in Lustre, but you know, there may be a lot of cache disk somewhere which is still being used. That's interesting. You get 116 nodes. Okay, 126. So 88. Yeah, I think we are because we are all hammering OS. We are all hammering the same IO system, the same file system. So you know, it's never quiet. So we may have been clashing with each other. But if you get 126, okay, so that's more than I would. I need to do these maybe on a quiet system, but it still looks like maybe. So you're getting 12 or 1612s or what? Okay, maybe it's more like 100 GB per second is the maximum. As I said, I've got a warning on this later on. The IO benchmarking is very difficult because of a whole bunch, and not least you're sharing the system with other users. But I think that was useful. It does, Elliot, you're absolutely right. It does depend on other users' use. It does depend on that, exactly. And so because we're all sitting here running, we're clashing with each other almost by definition. So that's interesting. Okay, so if there are no more questions, hopefully you found that interesting. And it is very early on in the Archer service, so these, you know, we're still finding out what the baseline numbers are. But I will save that and I'll tidy that up. Let's see. Somebody what did you get? So I've got these noted now. I will do a more complete study later on. But what I want to do now is the next lecture is an overview of how Mpio works. So this is, I'll go over this. Like I said, this used to be a course entirely about MPI-IO, but I wanted to just at least go through how MPI-IO works to give you a feeling for how these IO systems work. So I'm going to cover the basic MPI-IO model here. I'll cover the MPI-IO model, the basic file handling routine, setting the file view, which is MPI's terminology for saying which process owns which part of the file, and how you achieve performance. And it's the achieving performance which is useful, and that achieving performance comments apply to all IO libraries as well as MPI-IO. But I'll do this relatively quickly, because originally this course was to teach you to write MPI-IO, and we had MPI-IO exercises. Now I'm just using it as an example to discuss the issue, so I won't go in detail in the syntax. So MPI-IO and controller IO. Controller IO uses a single process for read and write. This requires a buffer to hold the entire file on the controller, and it's not scalable due to memory limits. In the Mpio model, each process describes what subsections of the file it owns. This is done using standard MPI data types. These are passed into the MPI-IO routines, and then the data is ultimately read and transferred directly or written. I've got read here. Written directly to local memory. There's no single large buffer, no explicit controller process. So MPI-IO is symmetric in the sense that, I mean, you don't know what it does under the hood, but there's no explicit controller process. So the MPI-IO approach is to open the file, set the file view, read or write data, and close the file. Now, if you were to design any IO library, you'd need to be able to open a file, read or write data, and close the file. It's kind of obvious. All the complexity is hidden in setting the file view. This is where the derived data types appear. This is where and I'll briefly cover at the end of the course what the analogies are for example, HDF5 and something called NetCDF. Now, this is actually a hangover from a previous lecture. Write is probably more important in practice than read. Exercises concentrate on read. That was when we actually had, I should fix this slide, when we actually had actual exercise where you wrote MPI-IO. So that's not actually relevant to this lecture. So to open a file, you do MPI file open. It's collective across a communicator. You give a file name. You give an info object, which is hints, but we'll not really talk about that. You can leave that as, you can just leave that as a null thing, and you get back a file handle. This is exactly analogous to opening a file in C when you get a file pointer, opening a file in Fortran when you get a unit number. But you specify file name, and you get a thing back called a file handle. Well, this is the Fortran thing. So attach the file to the file handle. It's analogous to C file pointer or Fortran unit number. Collective across the communicator, and the access modes are the usual things. You can create, read only, write only, or read write. So this is just how you open a file, and the important point is it's collective across the communicator, because we're going to be doing parallel IO to expect that all the processes in the communicator are going to be doing reading or writing, and you would normally you might have MPI call the communicator. Examples: MPI file handle, access mode is read only. Open across MPI code, the data file, the access mode, Mpio info null. The info allows you to specify hints and local configuration options and such like, but we're not going to use that. And the file handle, or in Fortran, it's just the same. And it's just a slight technicality for MPI IO. If you want to create as well as write, you need to add or combine these access modes. If you're doing write only and you want to create, you need to OR them together in C or add them together in Fortran. But that's just a slight technicality. Closing a file, file close, it's collected across the communicator, must be called by all processes that communicate. That's the obvious thing to do. I've got read here, but you can do write as well. Once you've opened a file, you do MPI file read all or write all, the file handle, a buffer count, the data type, and the status. So in the read, this just looks like a receive. So MPI the Io model is a bit like a receive. A read is like receiving from the file. This is a very similar syntax to MPI file, to MPI receive. You'd specify who you want to receive from, a buffer count, and a data type. If you're doing MPI file write, you would do exactly the same. You'd write, it would be like sending data. So this reads count objects of type data type from the file in each process, and it's collective across the communicator. It's very similar to fread or Fortran read. But you'll see here that this looks weird because every process is issuing the same, in this case, read operation, but you explicitly want them to read different data, okay? Actually, in between opening the file and issuing the read, you set the file view. And this is where you say, actually, this process is interested in or owns this section of data. So this read doesn't apply to the whole file. It only applies to a subsection which you've set with the file view. So the important point, so actually, you know, in my previous example, every process would do an MPI file write all of 4 double precision numbers, but they wouldn't all write to the same point in the file because they'd all have a separate, what MPI calls a file view. And so setting the file view, you do MPI file set view, you've got the file handle, you can specify an offset, a displacement. So you're saying, my view of the file starts this far into the file. That's normally for skipping a header block. So typically I'd set 0. The E type specifies the elementary data type, which is the building block of the file, which for us might be double precision numbers. The file type is this MPI data type, which says, and we can use which portion, that's the important one. That's where you specify which part of the file you own. Data rep specifies the format of the data, and there's an info for hints, but we'll not use that. We'll just use MPI info now. So the important ones here are data. Really is the file type. The data type is just what the file is made of, which will be MPI doubles, for example. The file type is the key one, which says I'm interested in these pieces of the file, not the whole file. So, for example, now I'm going to jump. If you imagine that what we're going to have to do is we're going to have to specify, in my 2D example, subarrays. We would want process 1 to say I've got the bottom left-hand corner, process 2 the top left, process 3 the bottom right, process 4 the top right. If you think about it, if we think of if I imagine I want to take a 3x2 subsection of a 5x5 array, okay, if I draw this in a certain way, it turns out to be a pattern like this. These are the important point is when you take subarrays of arrays, they're not contiguous in memory. It's different in C and Fortran because of the way column major, row major, and all that stuff. But the important point is MPI has a way of specifying this as a single data type. It has subarray data types. In memory, they actually have these strided patterns, but that's not particularly important. So MPI already had a mechanism for doing that. You may have come across vector types, which if you come on my MPI course, you'll see vector types, which allow you to specify these patterns, block, gap, block, gap, block, gap in memory. They're specified by a block length, a count, and a strike. They turn out to be inconvenient for a number of reasons. In particular, they don't generalize to 3 dimensions. So in fact, the data type which is most useful for regular data patterns like we're doing, like my benchmark, is a subarray data type. And actually, it's very, very simple. You say I've got how many dimensions, in this example 2, but in my example 3. An array of sizes is how big the array is. Array of subsizes is how big your local section is, where it starts, and you have to say, well, come back to order, are you C or Fortran, and you get back a new data type. So this new data type actually corresponds to a 3x2 subsection of a 5x5 array as a single data type. If you send one of them, the entire here for 6 entries. So this is quite specific to MPI, but other IO libraries will have different ways of specifying what the subsections are that you're interested in. But MPI uses subarray data types. So for example, if I wanted to do this in C or Fortran, I want to specify this 3x2 subsection of a 5x5 array. You see it's 3x2, but it starts here. The bottom left-hand corner is at 0, 1, 0, 1, at 1, 1. I would say in C, I've got my new data type is subarray 3x2. I have an array of sizes, subsizes, and starts, which are the size of the array is 5x4. Okay. The subsizes are 3x2. I want the 3x2 subarray, and I start at 2, 1. That's wrong. That's a typo. Okay, I don't start at 2, 1. I start at 1, 1. So that's a typo, which I've not noticed before. So that is a typo. I'll fix that. Apologies for that. Now what you do, you have to tell MPI whether you're in C or Fortran, because C and Fortran have these different definitions for column major and row major. But then it's quite simple. MPI type creates subarray, number of dimensions, which is 2, the array of sizes, which is 5x4, array of subsizes, which is 3x2, array of starts, start at 1, 1. The order is order C, and the array, say, contains MPI floats, and I get back this new subarray data type. So I've defined this subarray data type, which corresponds to this subsection of the big array, and I have to commit it. That's an MPI technicality. In Fortran, I need to fix this thing here as well. It's the same syntax. It's exactly the same syntax. The important point is that in our example here, to use MPI-IO. Oh, I'm getting a bit of feedback. Oh, no, not anymore. The yellow process has to define a subarray for the bottom left-hand corner, the blue process the top left, the red the top right, and the green the bottom right. And so, for example, the rank 1 file type would be this. So if you didn't understand the issue about file types, it doesn't really matter. There is a procedure which MPI calls MPI file set view, where the blue process 1 says, I am interested in elements 3, 4, 7, and 8. Now we do that by specifying a file type, which is of this format, blank blank data data blank blank data data, which is most easily created as an MPI type subarray. But once you've done the MPI file set view, rank 1's view of the file, it only sees this data. So if rank 1 says, I want to read 4 elements, it will read elements 3, 4, 7, and 8. So the file view is like a mask. You see nothing but your file view. Once you said, I'm interested in elements 3, 4, 7, and 8, that's all you see. So the reads and writes look very simple. You just read or write 4 elements. The fact that these are the top left-hand corner part of the array was because your file view masked out everything else. And so that you can then do linear reads. So if I, whoops. Sorry, I'm having a problem here. Can people still hear me?
Yes.
Yes.
And see me? Okay, I just had a slight problem. My display went blank. I don't know why, but I'm back. Sorry, but I thought the machine had died. It was just my display just went slightly funny. Okay, so where was I? Yeah, so you mask out this data, and then you can just do the linear reads. Now, so that's what we're, if you could be bothered to look at the Bench IO benchmark, it actually uses 3D subarrays. It just positions, it says, look, IO in this part of the array, IO in that part of the array. Okay, I'm having a bit of a problem here. Okay, fine. Fine. So the file type should tile the file. It's up to you. So rank 0 will specify that file type, which is that guy, those guys there. Rank 1 will specify that file type. Rank 2, this one. Rank 3, and you can see that together they tile the file. So when this rank 3 says it wants to read or write 4 elements, it writes these ones, but there's no clash. It's up to you to make sure they don't clash, actually. But so that is how MPI does the IO in this data phase. There's something called the MPI file set view, where it's up to you to specify MPI data types, which correspond to the yellow, the blue, the green, and the red subsections. But at least for these regular IO patterns, MPI subarray types are by far the easiest. But what's actually more important now, data representation, if you remember, I skipped over it a bit, but when you open a file, when you set a file view, you have a data representation. That can be native, internal, external 32. Fast as native, just raw bytes are written to a file exactly as in memory. That may not be portable between different systems. So most portable is external 32. This is weird. I would recommend native. I mean, to be honest, you know, IO is slow. You don't want to slow yourself down. You just want to get the data out to disk. So I would recommend, at least for Mpio, using the native representation, which just dumps the data raw onto disk with no conversion. So one of the reasons that I think I wanted to go through the MPI is the following slides apply equally to other MPI libraries. If you see, the command I gave you was called MPI file read all, or there would be MPI file write all. The all means it's collective. The all means that you're guaranteeing that at this point every process is calling the read or the write operation, and that's very important because it allows Mpio to do very clever optimizations. So, for example, if you just did MPI file write, the MPI library would have to say, okay, the yellow process wants to write this data. I have to be careful here because other people might be accessing the file. So it would probably have to lock the file, write this data, skip, write that data, then unlock it. Then rank 1 could come in and write its data. It's a whole lot of messing around. If you do MPI file write all, MPI says, okay, everybody's writing the data. So it can do clever things. It can say, because I know everybody's writing, the yellow and the blue process are both writing. That means I can collect that data together into a single block and do one big write. And then maybe combine the data from ranks 2 and 3 and do a single read and write. So collective routines can aggregate reads or writes for better performance. And this turns out to be absolutely crucial for parallel IO. It makes factors of 10, 100, 1,000 in performance, at least on Archer. I haven't benchmarked it in detail on Archer2, but it is absolutely crucial to do collective routines. Because if the IO library knows that if you just do MPI file read or write, or the equivalent non-collective call in your favorite IO library, it has to process them individually. It has to say, well, I have to probably lock the file, lock the OST so that no one else can access it, do my data, and then unlock it and then release it. And that's a nightmare. If you do read or write all, which is collective, it can say, everyone's doing it, so I know the yellow and the blue process, I can collect the data together and do one big write, a single gigabyte of data without all this horrible messing around. And so collective I/O is absolutely crucial in getting performance. So you should use collective calls, MPI file read all, MPI file write all, and there will be equivalents, and I'll mention them later for HDF5, and I also mentioned NetCDF. The info objects I'm not going to really cover. It allows you to specify things to do with the file system configuration when you open a file, but I think it's easier to do that within Lustre. So I think on Archer, it's easier to tune Lustre file system than use Mpio hints. So I tend to use these info to MPI info null and do all my tuning from the Lustre file system. I find that much more easy. So that was a bit of a run through. I didn't really have time to go into much detail, but the important point is the MPI-IO calls it deceptively simple. You just do read all, write all. The user must define appropriate file types. So when you do the set view, so each process sees its own correct part of the file, and that's the difficult part. And use collective calls whenever you can, enables the IO library to merge reads and writes, enables a small number of large IO operations, which has a huge effect on performance. And so that's really just a very, but I think the key slide is this slide, slide 20, where you see that you have defined your file type so that the yellow process knows it owns this, sorry, the MPI-IO library knows that the yellow process owns this data, and it can then analyze that pattern and say, okay, if the yellow process and the blue process are both writing, I can collect them together in an internal buffer and then do a single write to disk and do it very efficiently, and the same for read. So hopefully, I can't remember, let's look at what the timetable was. Actually, so I had this was supposed to be the practical now Mpio performance. I can share that sheet. So you'll see that we've now done an initial exercise where we worked out that 1 gigabyte, 1.2 gigabytes per second was the maximum from a single process. I should have done more here, maybe 2, 4, but we saw that you can get up to about, it looked like about 100 gigabytes per second. It looks like the OST's maxed out at about 6 or 8 gigabytes per second. But we did everything to the unstriped file. For MPI-IO, you want to start off with nodes equal and task per node equals 128, and just do local MPI-IO. But if we do this, it will write to all 3 directories. So what we're doing now is we're saying, look, how does striping? So first of all, you have to have done the striping correctly on the directories, LFS set stripe on the striped, unstriped, and full striped directories. But the basic thing to do is to do MPI-IO on 2, 4, and 8 nodes, on 1, 2, 4, and 8 nodes. But for each time, because we're not specifying a directory here, it will do all the directions, or write to the unstriped, the striped, and the full striped. So we're seeing that what we're trying to see. We saw that, well, we haven't checked, but I'm pretty sure that serial I/O won't benefit from striping. The question here is, can parallel I/O benefit from striping? And then we'll do that, and we can then look at the I/O rates. There's some other exercises here, but I think the most important thing would be to run this. What I'll do is I'll just check that I can get that to work. So I will share my. If there are any questions, please ask now. But so what I want to do is, are we seeing this now? Yep. So if I do that exercise, it would be nodes equals 1, task one is 128, and then Okay, I want to do, I'm saying 128 here, just some parameters. 128, 128, 128, which is a local size, and we want to do MPI-IO. So here, run that. Let's see if I'm running. I am. If I now look at unstriped, okay. Are there any files in here? There it is. So, for example, it's now onto the striped. You can see it's running. There's an Mpio.file. I removed the files after they've rewritten. Otherwise, we're going to run out of. I think it might have finished. Okay. So it ran, and we got total amount of data is 2 gigabytes. I'm running on one node, and it's this node here. Using the following IMS MPI, using the following stripings, all of them, MPI-IO. So you'll see that there was a small benefit from striping, but not very much. Okay, so we unstriped, I got 1.1. Striped, I got 1.8. So there is some benefit from striping. Remember, this thing here has 12 stripes, and you might hope that we get. Now we can come back to why that is, but I would like you to maybe go away and run those tests of 2, 4, and 8. You can even do 16. I would actually maybe do 16 nodes as well. Run those tests with 2, 4, 8, and 16 nodes, and then we can look at the data and see if we can understand it. So the output from this file is the formatting's a bit bad. There should be a space between there and there. So that relates to that. That's a bit poor, actually. I've not formatted this quite correctly. But are there any questions? What we'll do is we'll come back at this is a practical session now. We'll come back at 2 o'clock after lunch. So the practical session till 1, and then we'll come back at 2 and maybe discuss these results. I'm happy to answer any questions.